Hi everyone, today I want to show you a project I've been working on using reinforcement learning. I wanted to teach 5 AI agents how to play red light, green light. The goal wasn't just to beat the game, the goal was to see how much faster I could train the AI if I removed the graphics. I use an algorithm called PPO from the Stable Baselines 3 library. I actually wrote 2 versions of the code, a visual version and a headless version that runs purely on math. The visual version we can actually watch as the AI learns and trains after each iteration. So let's jump into the code and I'll explain how the architecture works. So first, let's look at the environment. This is where the rules of the game lives. In reinforcement learning, we have an observation space and an action space. Here at marker 1, I define the observation space. I'm not feeding the AI pixels because that's too slow. Instead, I'm feeding it vectors with 2 numbers, the color of the light and its position on the track. This simplifies the problem so the neural network can learn much faster. So if we scroll to marker 2, here's the most important part, the reward function. This is how the AI knows if it's doing a good job. I had a problem early on called the local minima, where the agents realized that if they just stood still, they wouldn't die. They were playing it way too safe. So I added a penalty here. If the light is green and they're waiting, I take points away. This forces the policy to be aggressive and actually race. So if we scroll down to marker 3, here's the visual bottleneck callback. This is a custom callback I wrote to render the game window. It allows us to watch the training, which looks cool, but it creates a massive bottleneck. This is a very big performance issue, actually. So let me run it and show it to you, and you guys will see what I'm talking about. So you can see the agents trying to figure it out. But look at the speed. It's locked to 60 frames per second. The CPU has to wait for the window to draw every single frame before it can calculate the next move. In machine learning, we want millions of steps. At this speed, it would take hours to get a good result. So let's switch to my fast training, which is the headless one. So to fix this problem, I created a headless environment. That's what we call when the code runs without a display. Here at marker 4, I stripped out all the Pygame code. This decouples the simulation from the rendering. Now the CPU can run as fast as the electricity allows. But since I can't see the game anymore, I needed a way to track progress. On marker 5, I built a console logger. It tracks the minimum streak on the team. Basically, if the worst player on the team is winning 10 times in a row, I know that the model has converged, because statistically, that means it has. So let me run this, and you guys will see how it works. So you see the terminal? It's processing thousands of steps per second. It's about 100 times faster than the visual version. The model's iteration through generations almost instantly. And see here, we're done. This is the victory lap. The code enters an inference phrase here at marker 6. This is where we turn the graphics back on, as you just saw, to see the result. And as you can see, the movement's perfect, and they've learned the pattern at the end. So this project really showed me the importance of optimization. By separating the training logic from the visual logic, I turned an overnight task into a 20-second task. This is pretty similar to how real-world AI is trained. You do the heavy lifting in a cloud, headless, then you just deploy the finished brain version to the robot. Thanks for watching.